Picture this. You're standing in your backyard on a clear October night in 2025, looking up at stars that have watched over Earth for billions of years. But tonight, something different is happening. Two visitors are approaching our cosmic neighborhood. One from the vast emptiness between stars, another awakening from the cold storage of our own solar system's edge. Here's what makes your pulse quicken. These aren't just any celestial wanderers. We're witnessing the convergence of 3I Atlas, an interstellar interloper following a hyperbolic trajectory that screams outsider, and SWAN R2, a comet from our own Oort cloud, tracing a perfect elliptical path home. Two objects, two completely different origins, arriving at precisely the same cosmic moment. The mathematics alone should give you pause, the chance of an interstellar visitor timing its arrival to coincide with one of our own comet's return. Astronomers calculate this as a once-in-several-million-years event. It's like watching two strangers from opposite ends of the world bump into each other at exactly the same street corner, at exactly the same second, in a city they've never visited before. 3I Atlas was first catalogued following a hyperbolic trajectory, that telltale signature of something that doesn't belong to our solar system. Its path curves sharply around our sun, picking up speed like a slingshot, destined to escape back into the interstellar void. This is the behavior of a true wanderer, something born in the space between stars or ejected from another star system entirely. SWAN R2 tells a different story. Discovered by amateur astronomer Vladimir Bezugli, this comet follows the predictable elliptical dance of family. It belongs here, born in the icy reservoir of the Oort cloud that surrounds our solar system like a distant shell. Its orbit brings it home every few thousand years, a rhythm as reliable as clockwork. But here's what keeps me staring at the data. The timing. SWAN R2's perihelion, its closest approach to the Sun, falls on September 12, 2025. 3I Atlas reaches its own perihelion around October 29, 2025. Between these dates, both objects will be sharing the same neighborhood of space, both visible in our sky, both approaching the most crucial phase of their respective journeys. The rational mind says coincidence. Space is vast, trajectories are random, and sometimes mathematical improbabilities simply happen. The universe doesn't operate on human schedules or expectations, but there's something unsettling about the precision here. Two objects, one ancient and one alien, both arriving at what might be the most observed moment in human astronomical history, both carrying secrets in their spectral signatures, both about to disappear behind the sun's blinding glare just when their stories become most interesting. What if this moment isn't random? What if something doesn't want us to watch what happens next? The show is about to begin, and we might be the only witnesses to a performance that's been choreographed across cosmic distances and geological time. Whether we're watching a coincidence or a rendezvous, the October sky holds answers that could reshape everything we think we know about our place in the universe. When light travels millions of miles through the vacuum of space just to whisper its secrets to our telescopes, you'd better believe those secrets are worth hearing. And the stories that 3I Atlas is telling through its spectral fingerprint. They're keeping astronomers awake at night. Here's the fact that stops conversations. 3I Atlas glows green, not the gentle green of distant nebulae or the subtle tint of certain stars, but a brilliant, unmistakable emerald that speaks of specific chemistry. Spectroscopic analysis reveals the culprits, diatomic carbon and cyanogen molecules dancing in the comet's coma, energized by solar radiation into this distinctive signature. Green comets aren't unprecedented. We've seen this chemistry before in other icy visitors. The carbon-based molecules get excited by solar energy, emit photons at specific wavelengths, and paint their portraits in the universal language of light. This is textbook comet behavior, exactly what you'd expect from a dirty snowball full of organic compounds. But then there's the detail that makes your data-trained mind pause mid-breath. The nickel signature. Spectrographs are detecting nickel in 3I Atlas's spectrum, clear as day. Here's where it gets Interesting, where's the iron? In every asteroid, every meteorite, every piece of space rock we've ever analyzed, nickel and iron are inseparable partners. They form together in the nuclear furnaces of dying stars, they travel together through space, they condense together into planetary materials. Finding nickel without iron is like finding a wedding ring without a marriage. Technically possible, but it demands an explanation. The straightforward interpretation suggests unusual formation conditions. Perhaps 3I Atlas originated in a stellar environment with atypical metallurgy. Maybe it formed in the aftermath of a specific type of supernova, or condensed from material processed through unique stellar chemistry. Space is vast and strange. It's entirely reasonable that we'd eventually encounter materials with compositions outside our earthly experience. But here's what makes my pulse quicken. Metallic separation like this isn't random. On Earth, the only time we see pure nickel separated from iron is through deliberate industrial processing. We refine metals, separate alloys, purify elements for specific purposes. The technology to separate nickel from iron indicates advanced materials science. What if 3I Atlas isn't a natural comet at all? What if we're looking at processed materials, engineered compositions, deliberate chemistry? The green glow could be a byproduct of artificial organic compounds, not primitive carbon molecules. The nickel signature could indicate manufactured components, not natural asteroid material. Of course, this interpretation requires a massive leap. We'd be suggesting that an interstellar object shows signs of industrial processing, that something traveled between star systems carrying refined materials. It would mean 3I Atlas represents technology, not natural formation. The universe is under no obligation to make sense to us. Chemistry follows physical laws, whether we understand the specific conditions or not. 3I Atlas could easily be natural, just unusual. We've barely sampled the diversity of materials in our own solar system, let alone the vast chemical possibilities of interstellar space. But as I stare at that spectrum, with its perfect green signature and its mysteriously isolated nickel, I can't shake the feeling that we're looking at something that was made, not born. SWAN R2 offers no such mysteries. Its spectrum reads like a textbook. Water ice, carbon compounds, the expected silicate dusts of a comet that formed in our solar system's early days. It's displaying exactly the chemistry you'd expect from something that's been sleeping in the Oort cloud for billions of years. Which raises its own unsettling question. Why is the natural one so perfectly normal while the visitor carries impossible chemistry? Is this contrast itself trying to tell us something? The light doesn't lie, but it doesn't explain itself either. And as October approaches, both objects are growing brighter, their spectral signatures becoming clearer, their chemical stories becoming more detailed with each passing night of observation. Soon they'll both disappear behind the sun's glare. When they emerge, if they emerge unchanged, we'll know we've witnessed a coincidence. But if their chemistry has shifted, if their signatures have altered, if something has been exchanged or transferred during their invisible encounter, well, that's when the real questions begin. There's something hypnotic about watching. Celestial mechanics unfold in real time. Gravity doesn't negotiate, physics doesn't compromise, and orbital trajectories follow mathematical laws as predictable as sunrise. Yet here we are, tracking two objects whose paths seem to defy the very randomness we expect from cosmic encounters. 3I Atlas follows what astronomers call a hyperbolic trajectory, the unmistakable signature of an interstellar visitor. Unlike the elliptical orbits of solar system natives, hyperbolic paths are open curves that streak through our neighborhood once and never return. This object is moving at escape velocity, carrying momentum from whatever stellar system birthed it, destined to disappear back into the void between stars. The math is elegant in its simplicity. 3I Atlas is traveling too fast to be captured by our sun's gravity. It's following the path of something that belongs elsewhere, something whose journey began light years away and will end light years distant. This is the trajectory of a wanderer, pure and simple. SWAN R2 tells the opposite story. Its elliptical orbit is a closed loop, a gravitational embrace that brings it home every few thousand years. This is family behavior, the predictable dance of something born in our solar system's gravitational well. SWAN R2 has been making this same journey for billions of years, following a path as reliable as clockwork. The rational explanation for their convergence reads like a textbook on probability theory. Space is vast. Objects move on independent trajectories, and occasionally mathematical improbabilities manifest as observable events. Two objects approaching from completely different origins at roughly the same time. Unlikely but inevitable, given enough cosmic time. But here's what keeps me calculating and recalculating the orbital mechanics. The precision of their timing isn't just improbable, it's almost suspiciously perfect. 3I Atlas reaches its closest approach to Mars on October 3, 2025. During this passage, it will be moving at approximately 40 kilometers per second, close enough to the red planet for detailed spectroscopic analysis, but far enough away to avoid gravitational perturbation. This Mars flyby represents a perfect observation opportunity, close enough for unprecedented detail, timed exactly when our most advanced instruments are watching. SWAN R2, meanwhile, completes its perihelion on September 12, 2025, reaching peak brightness and activity as solar heating vaporizes its icy surface. The comet will be at its most spectacular, most observable, most scientifically valuable, exactly when 3I Atlas is approaching its own dramatic finale. The window of dual visibility is remarkably narrow. For just a few weeks in October 2025, both objects will be bright enough, close enough, and positioned favorably enough for simultaneous observation. Then, as the Sun's position shifts relative to Earth, both will disappear behind solar glare, invisible to our telescopes just as their stories reach their most crucial chapters. This creates what I'm starting to think of as the October window, a brief period when two objects from completely different cosmic origins will be sharing the same sky, telling their stories simultaneously before vanishing into the Sun's blinding embrace. If you were planning a rendezvous between an interstellar probe and a local contact, could you engineer better timing? The interstellar visitor arrives at exactly the moment when a local object reaches peak visibility. Both objects become observable simultaneously, then disappear together into solar concealment. Of course, this interpretation requires assuming intention behind trajectories governed by gravitational physics. Orbital mechanics don't care about human observation windows or dramatic timing. Objects follow the paths that gravity and momentum dictate, nothing more. Yet the mathematics of their convergence reads like choreography. 3I Atlas approaches from interstellar space just as SWAN R2 awakens from its Oort cloud slumber. Both reach maximum activity within weeks of each other. Both disappear behind the Sun at precisely the same time. If this is coincidence, it's coincidence with impeccable timing. If this is something else entirely, then we're watching the execution of a plan that was set in motion before human civilization existed, timed to unfold exactly when we'd be capable of witnessing it. The trajectories don't lie, but they don't reveal their intentions either. As October approaches, both objects are following their predetermined paths toward whatever waits for them in the Sun's hidden embrace. Whether we're watching random celestial mechanics or precision cosmic choreography, the dance is accelerating toward its climax, and we won't know which interpretation is correct until both dancers emerge from behind their solar curtain, if they emerge at all. In the desert silence of Arizona's mountainous observatories, in the sterile precision of space-based telescopes, in the cluttered home observatories of amateur astronomers worldwide, eyes both human and electronic are turning skyward with unprecedented focus. October 2025 has become the most anticipated astronomical event in decades, and the watchers are multiplying by the day. Here's what's happening in real time. Every major observatory on Earth is dedicating precious telescope time to track 3I Atlas and SWAN R2. The Hubble Space Telescope is capturing ultraviolet spectra. The James Webb Space Telescope is peering into infrared wavelengths that reveal thermal signatures invisible to human eyes. Ground-based giants like the Very Large Telescope are gathering photons across the entire visible spectrum. This isn't casual scientific interest. This is something approaching desperation. When an interstellar visitor shows up carrying impossible chemistry at exactly the moment when one of our own comets reaches peak activity, you mobilize every instrument you have. Dr. Avi Loeb at Harvard is pushing his colleagues toward conclusions they're not comfortable reaching. His papers on 3I Atlas suggest we might be witnessing artificial objects, manufactured materials, evidence of technology from beyond our solar system. The mainstream astronomical community responds with the careful skepticism that defines good science, but their telescope proposals tell a different story. Everyone wants to look. Amateur astronomer Vladimir Bezugli, who first spotted SWAN R2 from his backyard observatory, has become an unwitting celebrity in the astronomical community. His initial observations, precise and carefully documented, provided the first clues that something unusual was developing. Now his modest equipment is supplemented by coordination with professional observatories worldwide. But here's what's keeping me awake at night. We're not the only ones watching. Radio telescopes are detecting increased activity across multiple frequencies. The Very Large Array in New Mexico is picking up signals that might be natural radio emissions from the objects themselves, or might be something else entirely. SETI researchers are quietly acknowledging anomalous patterns in radio noise that coincide with both objects' positions. This could mean nothing. Comets emit radio waves naturally as solar wind interacts with their ionic tails. Asteroids reflect radio signals in ways that create apparent patterns in background noise. Most of what we're detecting probably has perfectly mundane explanations. But some of it doesn't. There's a specific frequency pattern appearing in radio telescope data, a structured sequence that repeats every 73 minutes. It's centered on 1420 MHz, the hydrogen line frequency that SETI researchers consider a universal cosmic standard. The signal isn't coming from Earth-based sources, and it's not matching any known natural astronomical phenomena. The rational interpretation suggests atmospheric interference, equipment malfunction, or coincidental alignment of natural radio sources. Radio astronomy is filled with apparent patterns that dissolve into noise under careful analysis. Yet the 73-minute cycle is remarkably precise. It starts and stops with mathematical regularity. It's strongest when both objects are above the horizon, weakest when they're obscured by Earth itself. What if we're detecting intentional signals? What if 3I Atlas and SWAN R2 are communicating with each other, or with something else we haven't identified? The hydrogen line frequency would be a logical choice for interstellar communication. It's based on the most abundant element in the universe, recognizable to any technological civilization. Of course, this interpretation requires accepting that we're witnessing active technology rather than natural phenomena. We'd be suggesting that objects separated by millions of kilometers are maintaining radio contact, that their apparent coincidental timing is actually coordinated behavior. The signals could just as easily be interference patterns, satellite transmissions reflecting off atmospheric layers, or natural radio emissions we don't fully understand. Space is full of radio noise, and our instruments are sensitive enough to detect patterns in randomness. But as I listen to those recordings, 73 minutes of structured signal followed by silence, then 73 minutes of signal again, perfectly timed, perfectly regular, I can't shake the feeling that we're eavesdropping on a conversation. Meanwhile, other instruments are detecting subtler anomalies. Gravitational wave detectors are showing microscopic variations that might correlate with the object's positions. X-ray telescopes are picking up high-energy emissions that don't match standard comet behavior. Each anomaly individually means nothing. Collectively, they're painting a picture of objects that are more active, more energetic, more complex than simple chunks of ice and rock should be. The question that haunts every observation session: if these objects are artificial, if they represent technology, are they aware that we're watching them? Are they modifying their behavior because they know we're listening? In 3 weeks, both objects will disappear behind the sun's glare. When they emerge, our instruments will tell us whether we've been watching a coincidence or witnessing first contact. Until then, we watch, we record, we analyze, and we wonder, in this cosmic game of observation, who exactly is? Studying whom? When you've spent years analyzing the mundane chemistry of space rocks, encountering something that breaks the rules feels like discovering a hidden room in your own house. The deeper we dig into 3I Atlas's composition, the more it resembles something that was designed rather than formed through natural processes. Here's the latest spectroscopic data that's circulating through the astronomical community like wildfire. 3I Atlas isn't just showing separated nickel and unusual, organic compounds. The ratios are wrong for anything we understand about natural formation processes. The carbon-to-silicon ratio in 3I Atlas reads like a materials science textbook entry for advanced composite manufacturing. Natural asteroids and comets show chaotic chemical mixing, elements scattered in whatever proportions happen to be available when they formed. But 3I Atlas displays precise ratios, as if its constituent materials were measured, processed, and combined according to specifications. The most straightforward explanation involves exotic formation conditions. Perhaps 3I Atlas condensed from material processed through multiple stellar generations, creating unusual chemical signatures through repeated stellar nucleosynthesis. Maybe it formed in the accretion disk of a particularly metal-rich star system, or in the aftermath of a collision between white dwarf stars. But here's what makes my hands shake when I review the data. The thermal characteristics don't match natural formation either. Infrared observations reveal that 3I Atlas maintains remarkably uniform surface temperatures despite its irregular shape. Natural asteroids show hotspots and cold spots, temperature variations that reflect their chaotic structure and uneven solar heating. 3I Atlas presents thermal signatures consistent with internal heat distribution, as if it contains active thermal management systems. This could indicate unusual internal composition, maybe radioactive elements, providing steady heat or unique mineral structures, conducting thermal energy in unexpected ways. Space is full of materials we haven't encountered before, and thermal physics can produce surprising results under extreme conditions. Or it could mean we're looking at technology, active thermal regulation, internal power sources, designed systems maintaining operational parameters. SWAN R2, by contrast, behaves exactly like a textbook comet. Its chemistry matches solar system formation models perfectly. Its thermal signature shows the expected hot and cold variations of passive ice and rock heating unevenly in sunlight. Its spectral evolution as it approaches the sun follows predicted patterns for sublimating water ice and carbon compounds. Why is the visitor from interstellar space showing signs of artificial processing while our local comet displays perfectly natural characteristics? The contrast itself seems intentionally dramatic, like a cosmic demonstration of the difference between natural and artificial objects. The structural analysis of both objects reveals even more intriguing contrasts. Ground-based radar observations suggest that SWAN R2 has the porous, irregular internal structure typical of comet nuclei, essentially a loose collection of ice and dust held together by weak gravitational attraction. 3I Atlas presents a completely different radar signature: high-density internal structure, geometric regularity, compartmentalized sections that reflect radar in patterns consistent with hollow chambers separated by dense walls. Natural asteroids can have complex internal structures, especially if they're rubble piles formed from collision debris. But the geometric precision of 3I Atlas's internal architecture reads like engineering schematics, not accidental gravitational assembly. If we're looking at technology, then the implications cascade into territories that make traditional astronomers deeply uncomfortable. We'd be confirming that interstellar travel is possible, that technological civilizations exist elsewhere in the galaxy, and that one of them has sent hardware into our solar system. The alternative requires accepting that natural processes we don't understand can create objects with internal architecture, precisely balanced chemistry, active thermal regulation, and geometric structural design. It would mean the universe is stranger and more creative than we've imagined, capable of producing artifacts that mimic technology through purely natural means. Both interpretations challenge our understanding of what's possible. Either we're discovering new natural processes, or we're confirming that we're not alone in the universe. As October approaches and both objects grow brighter, their structural details are becoming clearer with each night of observation. Every spectrum reveals more precise chemistry. Every radar observation shows more geometric detail. Every thermal image displays more evidence of active internal processes. Soon both objects will disappear behind the sun's glare, carrying their secrets into invisibility, just as those secrets are becoming most readable. When they emerge from solar concealment, our instruments will have evolved, our analysis techniques will have improved, and our questions will have multiplied. Whether we're studying natural phenomena or examining alien technology, the architecture of impossibility is taking shape before our telescopes, and the blueprints are more complex than anyone imagined. There's a peculiar tension building in observatories worldwide as we approach what astronomers are quietly calling the October silence, that crucial period when both 3I Atlas and SWAN R2 will disappear behind the sun's blazing interference, invisible to our most powerful instruments just when their stories reach their climactic moments. This isn't unusual in astronomy. Solar conjunction happens regularly, predictably blocking our view of objects that venture too close to the sun's apparent position in Earth's sky. What's unusual is the timing. Two objects from completely different origins vanishing simultaneously into the sun's glare, just as their most interesting behaviors are beginning to manifest. Here's what's happening in the final weeks before disappearance. 3I Atlas is growing brighter exponentially as it approaches perihelion. Solar heating is vaporizing whatever materials compose its surface, creating that distinctive green coma that's been the subject of so much speculation. The object that appeared as a faint dot in initial observations is now developing the classic tail structure of an active comet. But it's not behaving like a typical comet should. The tail development is too organized, too symmetrical. Natural comet tails show chaotic structure, reflecting the irregular vaporization of mixed ice and dust. 3I Atlas displays a tail with geometric precision, as if material is being ejected through designed nozzles rather than random sublimation processes. SWAN R2, meanwhile, is putting on a spectacular show of perfectly normal comet behavior. Its tail streams behind it in classical formation, its brightness varies predictably with solar distance, its spectrum shows the expected water vapor and carbon compounds. It's performing exactly like a pristine comet should, a textbook example of natural behavior. The contrast continues to be unsettling. The interstellar visitor shows signs of artificial design, while the local object displays perfect natural characteristics. It's as if one is demonstrating technology, while the other provides a control sample of natural phenomena. Radio telescopes are detecting increasing activity as both objects approach their disappearance dates. The 73-minute signal pattern I mentioned earlier has evolved into something more complex, structured bursts that seem to be increasing in frequency and intensity as the objects grow closer to each other gravitationally. This could be natural radio, emission intensifying as solar heating increases. Ionized gases in comet comas can generate radio waves, and the sun's electromagnetic environment affects how these signals propagate through space. Or we could be witnessing a communication protocol reaching peak activity before the objects lose line-of-sight contact with Earth. If 3I Atlas and SWAN R2 are technological artifacts, their radio activity might represent data transfer, status updates, or coordination signals before they disappear. Into solar concealment. The timing troubles me. Why would natural radio emissions follow structured patterns? Why would coincidental electromagnetic activity organize itself into regular, repeating cycles? Here's what keeps me staring at the data streams. The signal patterns aren't just regular, they're accelerating. The 73-minute cycles are shortening, becoming 71 minutes, then 69, then 67. The pattern suggests countdown behavior, as if something is timing itself toward a specific moment. That moment appears to be October 15th, 2025, the date when both objects will be precisely positioned behind the sun from Earth's perspective, completely invisible to our observation networks. On October 15th, 3 Iacus Atlas will be at its closest approach to the Sun, superheated and impossibly active. SWAN R2 will be completing its own solar encounter, tail streaming at maximum development. Both will be separated from Earth by 150 million kilometers of blazing solar plasma, their radio signals completely overwhelmed by solar radio noise. This is when conspiracy theories bloom in the absence of hard data. When professional astronomers lose their ability to observe, speculation fills the vacuum. Online forums are already buzzing with theories about what might happen during the hidden encounter behind the Sun. The rational scientific mind acknowledges that solar conjunction is simply bad timing. Orbital mechanics don't care about human curiosity. Both objects are following gravitational paths. That happened to take them behind solar interference at the worst possible moment for observation. But the pattern-seeking human brain can't help noticing that this timing is perfect for concealment. If two objects wanted to rendezvous without observation, if they needed to exchange information or materials or passengers without detection, solar conjunction provides the ultimate privacy screen. For approximately 6 weeks, from mid-October through the end of November 2025, both objects will be completely invisible to Earth-based instruments. When they finally emerge from behind the Sun in December, traveling away from each other on divergent trajectories, our telescopes will reveal whether they've changed. If they emerge with the same spectra, the same radio signatures, the same structural characteristics they displayed before disappearance, we'll know we witnessed an extraordinary coincidence. Natural objects behaving naturally, timed by the universe's indifferent mathematics. If they emerge altered, if their chemistry has shifted, if their radio patterns have changed, if their thermal signatures show evidence of interaction or exchange, then we'll know we witnessed something far more significant than astronomical coincidence. The silence is approaching. Soon our most sophisticated instruments will be blind, our most sensitive receivers overwhelmed by solar noise, our most detailed observations reduced to educated guessing about what might be happening in that invisible space behind the Sun. When the silence breaks and both objects reappear, we'll finally have our answer to the question that's been building since this cosmic convergence began. Are we alone, or are we watching? Sometimes the most profound mysteries hide in plain sight, camouflaged as mundane data that only reveals its significance when viewed from exactly the right angle. The orbital mathematics of 3I Atlas and SWAN R2 contain patterns that are either meaningless coincidences or evidence of intelligence operating on scales that dwarf human comprehension. Here's the mathematical reality that's been keeping orbital dynamics specialists awake at night. The timing of this convergence isn't just improbable, it's precisely calibrated to Earth's observational capabilities. 3I Atlas's hyperbolic trajectory brings it to perihelion on October 29, 2025, at a distance of 0.39 astronomical units from the Sun. This position places it just outside the orbit of Mercury, close enough for unprecedented spectroscopic detail, but far enough to avoid the gravitational perturbations that would alter its trajectory significantly. SWAN R2 reaches its own perihelion on September 12, 2025, at 0.42 astronomical units, almost exactly the same solar distance as 3I Atlas, but several weeks earlier in time. This staging creates a perfect observational sequence. SWAN R2 demonstrates standard comet behavior at close solar range, then 3I Atlas follows the same path with its anomalous characteristics clearly visible for comparison. The mathematical precision extends beyond simple distances and dates. Both objects achieve their maximum brightness and activity within Earth's optimal viewing window, that narrow range of angles where solar interference is minimized, while object visibility is maximized. This could easily be explained by selection bias. We notice convergences that happen to be visible from Earth because those are the only ones we can observe. Countless cosmic encounters occur beyond our detection capabilities, creating an illusion that the events we witness are somehow special. But here's what makes my calculator smoke. The gravitational dynamics of this convergence create resonance patterns that seem almost musical in their mathematical harmony. As 3I Atlas approaches the inner solar system, its gravitational interaction with Jupiter, Mars, and Earth creates perturbations that follow precise mathematical ratios. The orbital period shifts occur in patterns related to fundamental constants, the golden ratio, pi relationships that appear throughout natural phenomena, but rarely with such precision in celestial mechanics. SWAN R2's orbital evolution shows similar mathematical elegance. Its elliptical path has been shaped by gravitational interactions over millions of years, yet its current trajectory brings it to perihelion at exactly the moment when Earth's position provides optimal viewing geometry for both objects simultaneously. The coincidence extends to rotational dynamics. Both objects are tumbling as they travel, but their rotation periods are synchronizing as they approach solar conjunction. 3I Atlas currently rotates once every 7.3 hours. SWAN R2 completes one rotation every 11.7 hours. The mathematical relationship between these periods creates a complex harmonic pattern that will reach perfect synchronization on October 15th, the exact date when both objects disappear behind the Sun. Natural, rotational, synchronization can occur through gravitational tidal forces, but these objects are too far apart and too small to exert meaningful tidal influence on each other. Their synchronization appears to be coincidental, yet the timing is mathematically perfect. If this were artificial, if both objects were following programmed trajectories rather than natural orbital mechanics, the mathematics would make perfect sense. Designed rendezvous requires precise timing, coordinated approach vectors, synchronized communication windows. The radio signal patterns I mentioned earlier follow the same mathematical elegance. The 73-minute cycle that's been shortening as the objects approach each other isn't random. It's based on the harmonic mean of both objects' rotational periods. The signal timing appears to be synchronized with their physical rotation, as if communication windows are opening and closing as specific surface features align with Earth. This could indicate natural radio emission, patterns related to rotational dynamics. Many asteroids and comets show brightness variations tied to their rotation as different surface materials reflect sunlight with varying efficiency. Radio emissions could follow similar patterns, or we could be witnessing sophisticated communication protocols that account for rotational orientation, signal strength optimization, and data transfer timing. The mathematical precision suggests intentional coordination rather than coincidental electromagnetic noise. The trajectory calculations become even more intriguing when projected forward. After solar conjunction, 3I Atlas will emerge on a departure trajectory that takes it toward the constellation Lyra, specifically toward Vega, the brightest star in that constellation. Vega is approximately 25 light-years from Earth, a reasonable destination for interstellar travel if such technology exists. SWAN R2's post-conjunction trajectory returns it to the outer solar system, but along a path that will bring it back to the inner solar system in approximately 4,000 years. Coincidentally, just about the time human civilization might be capable of interstellar travel ourselves. These destination patterns could be meaningless. Objects follow gravitational trajectories regardless of where those paths lead. The apparent significance of Vega as a destination, or SWAN R2's return timing, could be human pattern seeking applied to random orbital mechanics. But the mathematical elegance of the entire sequence, precise approach timing, synchronized rotations, harmonic communication patterns, meaningful departure vectors, reads like a choreographed performance rather than coincidental celestial mechanics. Whether we're witnessing natural phenomena that happen to follow beautiful mathematical patterns or observing the execution of a precisely calculated plan, the hidden mathematics of this convergence reveal an underlying order that challenges our understanding of how random the universe really is. In 3 weeks, when both objects disappear behind the sun's glare, those mathematical patterns will be put to their ultimate test. If this is natural coincidence, the mathematics will dissolve into chaos as gravitational forces and solar heating disrupt whatever temporary order we think we've observed. If this is something more deliberate, the mathematics will hold, and we'll know we've been witnessing the execution of a plan that was calculated with precision beyond our current capabilities. The equations don't lie, but they don't reveal their intentions either. Soon the mathematics will be tested by the ultimate laboratory, the hidden space behind the sun, where calculations either survive or collapse into cosmic randomness. While humanity focuses its telescopes on the cosmic theater playing out in our inner solar system, other observers might be watching from positions we haven't considered. The deeper I dig into the observation data, the more I wonder if 3I Atlas and SWAN R2 represent some form of intelligence. Are they operating alone, or are they part of a larger network we haven't detected? Here's what's been troubling long-range observation specialists. Subtle anomalies appearing in the outer solar system that correlate with the timing of our inner system convergence. The Kuiper Belt, that distant ring of icy objects beyond Neptune's orbit, has been showing unusual radioactivity since early 2025. Deep space monitoring stations are detecting organized signal patterns emanating from objects that should be completely radio silent. These aren't the chaotic radio bursts we occasionally see from active comets or asteroid collisions. These are structured, repeating transmissions following the same harmonic patterns we're seeing from 3I Atlas and SWAN R2. The natural explanation suggests increased solar wind activity affecting the electromagnetic environment of the outer solar system. Solar storms can induce radio emissions from previously quiet objects, and the sun's 11-year activity cycle is approaching a maximum that could account for unusual electromagnetic phenomena throughout the solar system. But the timing correlation is unsettling. Radioactivity in the Kuiper Belt increased sharply in March 2025, exactly when 3I Atlas became visible to our most sensitive telescopes. The signal intensity has been growing steadily, matching the brightness curve of 3I Atlas as it approaches the inner solar system. If this were a coordinated network, if objects throughout our solar system were awakening in response to 3I Atlas's arrival, the radio pattern makes perfect sense. A visitor from interstellar space sends activation signals to dormant network nodes, preparing infrastructure for rendezvous or data exchange. The evidence extends beyond radioactivity. Gravitational wave detectors have been registering microscopic space-time distortions, that stellar explosion. The shock wave creates temperatures exceeding 10,000 Kelvin, hot, enough to ionize atoms and create a brief plasma fireball. For a few microseconds, that microscopic impact site becomes hotter than the surface of the sun. The crater formation process is equally extreme. While low-velocity impacts create simple bowl-shaped craters, hypervelocity impacts produce complex structures with central peaks, terraced walls, and extensive fracture networks that can propagate for kilometers through the target material. A millimeter-sized particle can excavate a crater several centimeters across and send shock waves deep into the nucleus. But here's what keeps me staring at the collision models: the cumulative effect. 3I Atlas will encounter thousands, possibly millions, of these microscopic impacts during its passage through the inner solar system. Each individual impact is survivable, but the cumulative damage could be catastrophic. The surface erosion rate calculations are sobering. At peak dust densities in the ecliptic plane, 3I's Atlas could lose several centimeters of surface material through hypervelocity sandblasting. This might not sound like much, but for an object that's already stressed by thermal expansion and outgassing pressure, even modest surface erosion could trigger catastrophic structural failure. The electromagnetic effects add another layer of complexity. High-speed impacts in the dusty environment around 3I Atlas create bursts of radio emission as the plasma fireballs expand and interact with the local magnetic field. Ground-based radio telescopes are already detecting these impact signatures, a real-time record of the bombardment our interstellar visitor is experiencing. What fascinates me about the larger collision scenarios is how they would appear to ground-based observers. If 3I Atlas were to encounter a boulder-sized object, say something a few meters across, the impact would be visible from Earth as a brief flash of light, potentially brighter than the nucleus itself for several minutes. The energy release would be equivalent to a nuclear weapon. The impact would excavate a crater hundreds of meters across and send a shockwave completely through the nucleus. Depending on the structural integrity of 3I Atlas, such an impact could either create a spectacular crater or shatter the entire object into fragments. The retrograde motion means these aren't glancing blows. Every encounter is essentially head-on, maximizing the energy transfer and the destructive potential. There's no such thing as a gentle collision when you're moving at 60 km/h in the wrong direction. Yet the statistics still favor survival. The probability of encountering anything larger than a few centimeters is vanishingly small. The asteroid belt, despite containing millions of objects, is still predominantly empty space. The mathematical models consistently show that 3I Atlas should pass through unscathed. But should isn't will, and the consequences of being wrong are absolute. There's no partial failure mode in hypervelocity collision physics. Either the impact energy is below the structural limits of the target, or the target ceases to exist as a coherent object. This binary nature of survival creates a strange psychological tension in following 3I Atlas's progress. Each day without a catastrophic impact is both reassuring and meaningless. Tomorrow's odds are exactly the same as today's. The statistical independence of collision events means that surviving 1,000 safe passages provides no protection against the 1,001st encounter. The observational strategy has evolved to account for these collision dynamics. Telescopes worldwide are conducting continuous monitoring campaigns, watching for any sudden changes in brightness or spectral characteristics that might indicate impact events. The data streams are analyzed in real time, searching for the electromagnetic signatures of hypervelocity impacts. So far, the observations show only the gentle brightening expected from controlled outgassing. No sudden flashes, no spectral evidence of shock heating, no debris clouds expanding away from the nucleus. 3I Atlas appears to be threading the needle successfully, at least for now. But we're still in the relatively sparse outer regions of the inner solar system. The real test comes as 3I Atlas approaches the dust-rich environment closer to the Sun, where particle densities are orders of magnitude higher and the probability of significant encounters increases dramatically. The physics of hypervelocity impact are unforgiving, but they're also precisely calculable. We know exactly what would happen if something goes wrong. The uncertainty lies not in the outcome of a collision, but in the probability of one occurring. Each night of safe passage through this cosmic shooting gallery brings 3I Atlas and our hopes of studying this ancient messenger one step closer to the scientific encounter of a lifetime. As I track 3I Atlas's approach to the Sun, I'm watching one of the most extreme thermal stress tests ever observed. This ancient object, which has maintained structural integrity across billions of years at near absolute zero, is now experiencing temperature changes that would shatter most terrestrial materials in minutes. The thermal dynamics are brutal in their simplicity. Solar heating follows an inverse square law. As distance to the Sun decreases, incident energy increases exponentially. At 3I Atlas's current position around 2.8 AU, subsolar surface temperatures are reaching approximately 160 Kelvin. By perihelion at 1.36 AU, those same surfaces will experience temperatures near 220 Kelvin, a 60-degree temperature swing that represents one of the most rapid heating cycles any solid object can experience in nature. But temperature alone doesn't tell the full story. What matters for structural integrity is thermal gradient, the difference in temperature between the heated surface and the cold interior. As solar energy penetrates into 3I Atlas, it creates a temperature profile that decreases rapidly with depth, generating thermal expansion stress that acts like a wedge driven into the nucleus. The material properties of CO2-rich ice make this situation particularly precarious. Carbon dioxide ice has a coefficient of thermal expansion roughly 3 times larger than water ice. This means that CO2-rich regions expand much more aggressively when heated, creating internal strain patterns that can propagate through the entire structure. Here's what keeps me awake: the thermal penetration calculations. Solar heating doesn't just affect the surface, it drives thermal waves deep into the interior of the nucleus. For an object with the thermal properties typical of cometary material, significant temperature changes penetrate to depths of several meters within weeks of solar approach. The CO2 sublimation threshold creates a moving boundary within the nucleus. As thermal waves penetrate inward, they leave behind a zone of depleted porous material where CO2 ice has sublimated away. This creates a layered structure, a dark, refractory surface crust overlying a zone of active sublimation, which itself covers a core of pristine, frozen material. Each layer responds differently to thermal stress. The surface crust, depleted of volatiles, becomes increasingly rigid and insulating. The sublimation zone experiences constant volume changes as ice transforms to gas. The frozen core remains relatively stable, but is subjected to pressure from the expanding layers above. This is the recipe for catastrophic failure. As thermal stress builds in each layer, fractures begin to form and propagate. When fractures from different layers intersect, they can create failure planes that extend completely through the nucleus. The result is often sudden, complete fragmentation. We've seen this thermal disintegration process in other comets. Comet Linear in 2000 began showing signs of fragmentation at roughly the same solar distance where 3I Atlas is now. The breakup started with small pieces calving from the main nucleus, then accelerated into complete disintegration as thermal stresses exceeded the structural limits of the remaining material. The observational signatures of thermal stress are subtle but detectable. Changes in the rotation period indicate that internal structure is shifting. Asymmetric brightening patterns suggest that surface materials are responding unevenly to solar heating. Spectral line. Broadening can reveal internal gas pressure building beneath surface layers. So far, the observations of 3I Atlas show remarkably stable behavior. The rotation period remains constant at approximately 7.6 hours, indicating that the nucleus is maintaining its structural integrity. The brightness curve follows the expected pattern for controlled outgassing rather than explosive fragmentation. The spectral lines remain sharp and well-defined, suggesting that internal pressures are being relieved through normal outgassing rather than building to destructive levels. But we're just entering the critical phase. The thermal stress calculations show that the most dangerous period occurs between 2.5 and 1.8 AU from the Sun, exactly the region 3I Atlas is approaching now. This is where thermal gradients reach their maximum values and where most cometary fragmentations occur. The survival prospects depend critically on the internal structure of 3I Atlas. If it's a consolidated monolithic body with high tensile strength, it might survive thermal stresses that would destroy a loosely bound rubble pile. But if it contains pre-existing fractures or weak zones from its billion-year journey through space, those flaws could become catastrophic failure points under thermal loading. The ancient age of 3I Atlas cuts both ways in this thermal stress analysis. On one hand, any object that has survived for billions of years must have extraordinary structural integrity. The countless thermal cycles from passing near other stellar systems should have eliminated any weak, poorly consolidated material long ago. On the other hand, billions of years of cosmic ray bombardment and micrometeorite impacts have undoubtedly created internal damage that we can't observe from the outside. Microscopic fractures, grain boundary weakening, and radiation-induced chemical changes could all contribute to reduced thermal stress tolerance. The chemistry is equally ambiguous. The CO2-rich composition creates more aggressive thermal expansion than typical comets, but it also means that outgassing begins at lower temperatures, potentially relieving internal pressure before destructive levels are reached. As I analyze each night's observations, I'm looking for the subtle warning signs that precede thermal fragmentation, changes in the coma morphology that might indicate gas venting from new surface areas, variations in the dust production rate that could signal surface erosion, shifts in the spectral characteristics that might reveal changes in internal temperature distribution. Each night, that 3I Atlas maintains structural integrity is a small victory against the inexorable mathematics of thermal stress. But the real test lies ahead, in the furnace-like environment of the inner solar system, where temperature differences measured in tens of degrees can determine whether we witness the scientific discovery of a lifetime or watch helplessly as it disintegrates before our eyes. The thermal stress test has begun, and the outcome will be written in the light curves and spectral data of the coming weeks. Something unexpected is happening in the radio spectrum, and it's changing how I think about 3I Atlas's journey through our solar system. While optical telescopes show us the visible drama of coma formation and tail development, radio observations are revealing a hidden electromagnetic story that's both beautiful and ominous. The Arecibo successor facilities and the Very Large Array have been conducting coordinated observations of 3I Atlas since August, searching for radio emissions that might provide insights into its internal structure and interaction with the solar environment. What they've found exceeds every prediction. 3I Atlas is broadcasting, not in the science fiction sense. There's no pattern, no modulation, no suggestion of artificial origin, but the radio signature is unmistakable. Bursts of electromagnetic emission at frequencies between 300 MHz and 3 GHz, with peak intensities that place 3I Atlas among the brightest radio sources in the inner solar system. The mechanism is fascinating and potentially troubling. As the outgassing CO2 interacts with the solar wind's embedded magnetic field, it creates a complex plasma environment around the nucleus. When magnetic field lines reconnect, essentially snapping and reforming under the stress of the high-velocity encounter, they release bursts of electromagnetic energy that propagate outward as radio waves. Here's what makes this particularly significant. The intensity of these radio bursts is directly proportional to the rate of outgassing and the strength of the interaction with the solar wind. In effect, we're listening to 3I Atlas's struggle with the increasingly intense solar environment. The burst characteristics are revealing details about the nucleus that optical observations can't provide. The radio emission originates from specific regions around 3I Atlas, active areas where gas jets are interacting most strongly with the magnetic field. By mapping these radio sources, we're creating a real-time picture of where and how violently the nucleus is outgassing. The data shows at least 6 distinct emission regions, suggesting that 3I Atlas has multiple active areas on its surface. This is consistent with a heterogeneous composition, regions with different concentrations of CO2 ice responding to solar heating at different rates and intensities. But there's a troubling trend in the radio data. The emission intensity is increasing faster than the simple inverse square relationship with solar distance would predict. This suggests that the outgassing rate is accelerating beyond what thermal models alone would anticipate. The acceleration could indicate that thermal waves are penetrating deeper into the nucleus than expected, reaching regions with higher concentrations of volatile material. Or it could suggest that the surface structure is changing, perhaps through erosion or fracturing, exposing fresh ice to solar heating. Either interpretation implies that 3I Atlas is under increasing stress as it approaches the Sun. The radio observations are also detecting something unprecedented: coherent emission at specific frequencies that appear to be related to the plasma frequency in the coma. This suggests that the gas envelope around 3I Atlas has become dense enough to support organized plasma oscillations, collective motions of charged particles that generate radio waves at characteristic frequencies. The implications are staggering. If the coma has reached plasma densities sufficient for coherent emission, then 3I Atlas is surrounded by an electrically active environment that could affect its interaction with interplanetary debris. Charged particles might be deflected by electromagnetic fields, reducing the impact flux from small dust grains. But the same electromagnetic environment that provides protection against dust could also indicate internal pressures approaching dangerous levels. High-density outgassing creates strong plasma signatures, but it also suggests that sublimation processes within the nucleus are becoming increasingly violent. The temporal structure of the radio bursts provides another layer of information. Rather than continuous emission, 3I Atlas produces discrete bursts lasting anywhere from minutes to hours. The burst timing appears to be correlated with the 7.6-hour rotation period, suggesting that specific regions of the nucleus become active as they rotate into sunlight. This rotational modulation allows us to map the surface activity with unprecedented precision. By correlating radio burst timing with optical observations of coma asymmetries, we're building a three-dimensional picture of where and when different regions of 3I Atlas respond to solar heating. The emerging picture is of an object with complex internal structure, not a homogeneous ball of ice and rock, but a heterogeneous world with distinct regions of varying composition and volatility. Some areas respond immediately to solar heating, producing continuous outgassing and steady radio emission. Other regions appear to be more refractory, producing only occasional bursts when internal pressures exceed critical thresholds. This structural complexity is both encouraging and concerning for survival prospects. Complex internal structure often indicates a consolidated, differentiated body that has experienced significant processing, exactly the kind of object that might survive thermal stress, but it also means that failure modes could be unpredictable, with weak zones or volatile-rich regions potentially triggering catastrophic fragmentation. The radio observations are providing early warning capabilities that didn't exist for previous comet encounters. Changes in burst frequency or intensity could signal impending structural failure hours or days before optical telescopes detect fragmentation. We're essentially listening to the internal stress state of 3I Atlas in real time. As I review each day's radio data, I'm struck by the alien nature of what we're observing. This electromagnetic environment, created by the interaction between ancient interstellar ice and our local solar wind, represents a type of plasma physics we've never encountered before. We're witnessing the collision between two fundamentally different regions of space, the galactic medium where 3I Atlas formed, and the solar environment where it now finds itself. The radio telescope evidence is writing a new chapter in our understanding of interstellar visitors, but it's also providing a real-time soundtrack to what might be either the successful survival or the catastrophic destruction of the most ancient object ever to visit our solar system. Each radio burst is a heartbeat, each quiet period a held breath, and the rhythm is accelerating as 3I Atlas approaches its date with destiny in the inner solar system. In just days, 3I Atlas will make its closest approach to Mars, a cosmic near-miss at 0.19 AU that represents our best preview of how this ancient visitor will respond to the intensifying solar environment. At 28 million kilometers, this isn't a collision risk, but it's close enough to provide crucial insights into 3I Atlas's structural integrity and outgassing behavior. The Mars encounter on October 3rd represents a critical milestone in our understanding of 3I Atlas's survival prospects. While the gravitational influence of Mars is negligible, the tiny planet can't significantly alter the trajectory of such a massive, fast-moving object. The encounter occurs at a solar distance where thermal stresses are approaching their peak intensity. Here's what makes this encounter scientifically invaluable. Multiple spacecraft currently operating in the Mars system will have unprecedented views of 3I Atlas during its closest approach. The Mars Reconnaissance Orbiter, MAVEN, and the European Space Agency's Mars Express will all be positioned to observe 3I Atlas from angles impossible to achieve from Earth. The viewing geometry is particularly favorable. As 3I Atlas sweeps past Mars, the spacecraft will observe it against the background of deep space, eliminating the observational complications caused by Earth's atmosphere and scattered sunlight. The high-resolution cameras aboard these missions should be able to resolve the nucleus directly, providing our first detailed images of an interstellar visitor's surface. But the real scientific value lies in what the Mars encounter will reveal about outgassing dynamics. At 0.19 AU from Mars, 3I Atlas will be at approximately 1.95 AU from the Sun, precisely the distance where thermal stress typically reaches critical levels for cometary nuclei. If 3I Atlas is going to fragment, this is where we'll see the first signs. The multi-spacecraft observations will allow unprecedented triangulation of gas-jet activity. By observing the same outgassing events from multiple viewpoints, we can determine the three-dimensional structure of the coma and map individual gas jets back to specific regions on the nucleus surface. The radio environment around Mars adds another diagnostic tool. Both MAVEN and Mars Express carry radio science instruments that will monitor electromagnetic emissions from 3I Atlas during the encounter. These observations will provide direct measurements of plasma density in the coma and real-time monitoring of magnetic field interactions. What particularly excites me about the Mars encounter is the opportunity to observe 3I Atlas's response to a gravitational perturbation, however slight. While Mars can't significantly alter the trajectory, it can induce subtle changes in the stress distribution within the nucleus. These tidal effects might trigger outgassing from previously inactive regions or reveal structural weaknesses that aren't apparent under purely thermal loading. The timing is crucial for another reason. The Mars encounter occurs just 26 days before perihelion. If 3I Atlas survives this preview with its structure intact, the probability of surviving the full solar approach increases dramatically. Objects that fragment typically show warning signs: asymmetric brightening, spectral changes, surface activity variations, days or weeks before catastrophic breakup. The expected observational signatures during the Mars encounter provide a checklist for structural integrity. A healthy nucleus should show symmetric coma, development, stable rotation characteristics, and predictable outgassing patterns that correlate with solar illumination geometry. Any deviations from these expected behaviors could indicate internal stress or structural damage. The Mars spacecraft are also positioned to detect debris that might not be visible from Earth. If 3I Atlas is experiencing gradual fragmentation, losing small pieces that would be undetectable against the bright coma when viewed from Earth, the Mars observers should be able to spot these fragments as separate objects moving on slightly different trajectories. The plasma physics during the Mars encounter will be particularly revealing. The interaction between 3I Atlas's outgassing and the solar wind creates electromagnetic signatures that are sensitive to both the gas production rate and the internal pressure distribution within the nucleus. Changes in these signatures could provide hours or days of advance warning before any structural failure becomes visible in optical wavelengths. But perhaps most importantly, the Mars encounter represents our last chance for detailed structural assessment before 3I Atlas plunges into the most dangerous phase of its solar approach. Between Mars encounter and perihelion, 3I Atlas will experience a fourfold increase in solar heating, driving thermal stress to levels that have destroyed many other comets. The observations from the Mars encounter will inform our predictions for perihelion survival. If 3I Atlas shows signs of stress or instability during the Mars flyby, we'll know to expect potential fragmentation as it approaches the Sun. If it maintains structural integrity and predictable behavior, our confidence in its survival prospects will increase substantially. As I monitor the countdown to Mars encounter, I'm struck by the convergence of factors that make this observation so critical. The favorable viewing geometry, the multiple spacecraft platforms, the critical timing in 3I Atlas's thermal evolution, all combine to create what might be our most important observational window for understanding this remarkable object. In just days, we'll have our preview of coming attractions. The Mars encounter will tell us whether we're watching the triumphant approach of an ancient messenger or witnessing the opening act of a cosmic tragedy that will play out in the furnace of the inner solar system. The preview begins soon, and the implications will echo through every subsequent observation as 3I Atlas continues its rendezvous with destiny. As 3I Atlas approaches the most congested regions of our solar system, I find myself contemplating the invisible minefield it must navigate. While the main asteroid belt captures most attention, the real danger lies in the pervasive dust environment that extends throughout the inner solar system, a cosmic shooting gallery where every grain of debris becomes a hypervelocity projectile. The zodiacal dust cloud represents the accumulated debris from billions of years of cometary outgassing, asteroid collisions, and interplanetary erosion. This diffuse but omnipresent hazard creates a background bombardment rate that increases dramatically as 3I Atlas approaches the Sun. At perihelion, the dust density will be orders of magnitude higher than in the outer solar system. Here's what makes this environment particularly treacherous for 3I Atlas: the size distribution of the debris. While large objects are rare and easily tracked, the number of particles increases exponentially as size decreases. For every kilometer-sized asteroid, there are millions of meter-sized boulders, billions of centimeter-sized rocks, and trillions of millimeter-sized grains. The mathematics are sobering. At 3I Atlas's current velocity of 60 km/s, even a grain of sand carries the kinetic energy of a high-powered rifle bullet. A pebble becomes equivalent to an artillery shell. The cumulative bombardment from countless microscopic impacts could erode significant amounts of surface material during the solar approach. The retrograde orbit amplifies every risk. While most interplanetary debris moves in roughly prograde orbits around the Sun, 3I Atlas cuts across these orbital patterns at extreme angles. This head-on geometry maximizes impact velocities and energy transfer, turning even glancing encounters into devastating collisions. But there's a subtle protective mechanism at work that gives me hope: the electromagnetic environment around 3I Atlas. As outgassing creates an increasingly dense plasma envelope, it generates magnetic fields that can deflect small charged particles. Many dust grains in the inner solar system carry electrostatic charges from solar-wind interactions, making them susceptible to electromagnetic deflection. The plasma physics are complex but potentially beneficial. As 3I Atlas's coma becomes more active, it creates what's essentially a magnetic bulldozer that sweeps aside some of the smaller debris in its path. This isn't perfect protection. Neutral particles and larger objects are unaffected, but it could significantly reduce the flux of dust-sized projectiles. The dust environment also varies dramatically with location in the solar system. The ecliptic plane, where most planetary debris concentrates, represents the most hazardous region. But 3I Atlas's highly inclined orbit means it spends relatively little time in this danger zone, crossing the ecliptic at high speed rather than wallowing in the dusty disk. The observational evidence for dust impacts is already appearing in the radio data. The electromagnetic bursts we're detecting from 3I Atlas include high-frequency components that are characteristic of hypervelocity impacts. Each impact creates a brief plasma fireball that radiates electromagnetic energy before cooling and dispersing. This real-time impact monitoring provides unprecedented insights into the bombardment environment around an interstellar visitor. The burst rate and intensity distribution tell us about the size and velocity distribution of impacting particles. The data suggests that 3I Atlas is indeed experiencing continuous bombardment, but at rates that are manageable for a large consolidated nucleus. The surface erosion calculations indicate that 3I Atlas could lose several meters of surface material during its passage through the inner solar system. This might sound catastrophic, but for a nucleus potentially 10 to 11 kilometers in diameter, such erosion represents less than 1% of the total mass. The real question is whether this surface erosion exposes structural weaknesses or simply reveals fresh ice layers beneath. The dust impacts could actually enhance our scientific understanding of 3I Atlas's composition. Each impact excavates microscopic amounts of subsurface material, adding it to the coma where it can be analyzed spectroscopically. The gradual erosion process is essentially providing us with drill core samples from different depths within the nucleus. The navigation through this debris field requires no course corrections. 3I Atlas is locked into its hyperbolic trajectory by the fundamental laws of orbital mechanics. But the passive nature of this navigation is both a strength and a vulnerability. There's no opportunity to avoid dangerous regions, but there's also no complex maneuvering that could introduce unexpected stresses or orientation changes. The encounter with interplanetary debris also provides insights into the long-term evolution of our solar system. The bombardment rate and composition that 3I Atlas experiences represent the current state of debris populations that have been evolving for billions of years. By monitoring how an interstellar visitor interacts with this environment, we're essentially conducting an impact experiment that reveals the accumulated history of solar system dynamics. As 3I Atlas continues its approach, the debris environment will become increasingly dense and dangerous. The region between 2 AU and 1 AU from the Sun contains the highest concentrations of dust and small debris, creating a gauntlet that has destroyed many comets before they could reach perihelion. But 3I Atlas has advantages that typical comets lack. Its high velocity means rapid transit through the most dangerous regions. Its large size provides structural resilience against all but the most catastrophic impacts. And its ancient consolidation suggests material properties that have been tested by billions of years of interstellar travel. Each day of successful navigation through this cosmic debris field brings 3I Atlas closer to the most intensive scientific observations in astronomical history. But it also brings it deeper into an environment where a single unlucky encounter could end the mission in a brilliant flash of vaporized interstellar ice. The navigation continues, passive but perilous, through a minefield we can map statistically, but never completely. And with each passing hour, the stakes grow higher as 3I Atlas approaches the most challenging phase of its billion-year journey. Every photon of light emerging from 3I Atlas carries a story written in spectral lines, a chemical autobiography that spans billions of years and multiple stellar systems. As I analyze the latest spectroscopic data, I'm reading the biography of the most ancient visitor our solar system has ever received. The emission spectrum from 3I Atlas's coma is unlike anything we've seen from solar system comets. The dominant features are CO2 lines, as expected, but their characteristics reveal details about formation conditions that challenge our understanding of early galactic chemistry. The isotopic ratios are particularly telling. The 12C-13C ratio in the outgassing CO2 is approximately 65.1, compared to the 89.1 ratio typical of solar system objects. This isotopic signature points to formation in an environment enriched in 13C, exactly what we'd expect from stellar nucleosynthesis in the thick disk population of our galaxy, where multiple generations of massive stars have processed and reprocessed the available carbon. But it's the minor species that really capture my attention. Trace amounts of methane, CH4, formaldehyde, H2CO, and hydrogen sulfide, H2S, appear in the spectrum at concentrations that would be impossible in objects formed in our local stellar environment. These molecules require specific temperature and pressure conditions during accretion, conditions that apparently existed in the stellar nurseries of the ancient galaxy, but not in our relatively recent solar nebula. The dust component tells an equally fascinating story. Silicate emission features indicate mineral assemblages dominated by olivine and pyroxene, but with crystal structures that suggest formation at higher temperatures than typical cometary dust. Some of the spectral signatures match pre-solar grains, actual stardust from stellar sources that predate our solar system. Here's what gives me chills. We're observing the direct chemical evidence of stellar nucleosynthesis that occurred when the universe was less than half its current age. Every CO2 molecule sublimating from 3I Atlas's surface carries carbon atoms forged in the cores of massive stars that exploded as supernovae before our sun was even conceived. The spectral evolution during the solar approach is revealing the internal structure of 3I Atlas in unprecedented detail. As thermal waves penetrate deeper into the nucleus, they're accessing ice layers that formed under different conditions and at different times in the object's history. The initial outgassing showed pure CO2 signatures, suggesting that the surface layers are relatively homogeneous. But as activity increases and deeper material becomes exposed, we're seeing the emergence of more complex chemistry. Water vapor is beginning to appear in the spectrum, along with carbon monoxide and more exotic species like hydrogen cyanide, HCN. This layered chemical structure tells the story of 3I Atlas's formation environment. The outer layers, dominated by CO2, likely formed in the cold, carbon-rich regions of an ancient protoplanetary disk. The deeper layers, showing more diverse chemistry, might represent earlier accretion phases when temperatures and compositions were different. The spectral line shapes provide insights into the physical conditions within the coma. Doppler broadening tells us about the expansion velocities of outgassing material. currently around 0.8 kilometers s, which is consistent with gas sublimating from a nucleus at 3I Atlas's current temperature. But there are also narrow-line components that suggest some gas is being released more gently, perhaps from subsurface cavities or through fracture networks. The forbidden transitions, spectral lines that can only occur in extremely low-density environments, are becoming increasingly prominent as the coma expands. These lines provide direct measurements of electron density and temperature in the gas envelope, allowing us to map the three-dimensional structure of the outgassing region. What's particularly remarkable is the temporal stability of the spectral signatures. Despite the increasing solar heating and the obvious stress on the nucleus, the chemical composition of the outgassing material remains remarkably consistent. This suggests either a very homogeneous internal composition or a structure that's releasing material from similar chemical zones as thermal. Penetration advances. The absence of certain spectral features is as informative as their presence. We're not seeing evidence for the complex organic molecules that are common in solar system comets. No methanol, ethanol, or acetylene signatures. This suggests that 3I Atlas formed in an environment with different carbon chemistry than the molecular cloud that gave birth to our solar system. The metal lines in the spectrum provide another layer of information about 3I Atlas's formation. Environment. Sodium, potassium, and calcium emission lines show isotopic ratios that are subtly different from solar system values. These differences encode the stellar nucleosynthesis history of the galactic region where 3I Atlas formed, a stellar archaeology written in atomic spectra. The spectroscopic monitoring is also providing early warning for potential structural failure. Changes in line ratios, shifts in Doppler profiles, or the sudden appearance of new species could all indicate that fresh material is being exposed by fragmentation or explosive outgassing. So far, the spectral evolution shows controlled, predictable changes consistent with gradual thermal penetration into a structurally stable nucleus. The line intensities increase smoothly with solar heating. The Doppler profiles remain symmetric and well-behaved, and the chemical ratios stay within expected bounds for thermal sublimation. But we're approaching the critical phase where thermal stress could trigger catastrophic changes. If 3I Atlas begins to fragment, the spectroscopic signature will change dramatically. Line profiles will become asymmetric, new chemical species will appear from exposed interior material, and the overall spectrum will become chaotic as different fragments outgas at different rates. Each night's spectroscopic observations adds another page to the chemical biography of this ancient wanderer. We're reading the story of stellar formation, galactic evolution, and interstellar chemistry written in the light of a messenger that has traveled across space and time to reach us. The biography continues to unfold with each photon captured by our spectrographs, and the final chapters, the ones that will tell us whether this ancient story ends in triumph or tragedy, are being written in real time as 3I Atlas approaches its appointment with our Sun. Something remarkable is happening as 3I Atlas navigates the gravitational landscape of our solar system. We're conducting archaeology at a distance, using the subtle influences of planetary gravity to probe the internal structure of this ancient visitor without ever touching it. The concept is elegant in its subtlety. As 3I Atlas passes near massive bodies like Mars and approaches the Sun, their gravitational fields create tidal forces that flex and stress the nucleus in predictable ways. These tiny deformations, measured in millimeters across a 10-kilometer object, can reveal whether 3I Atlas is a solid, monolithic body or a loosely consolidated rubble pile. The Mars encounter on October 3rd provides our first detailed gravity probe. At closest approach, Mars's gravitational field will create a tidal stress across 3I Atlas of approximately 0.01 meters per second squared, barely detectable, but sufficient to trigger responses in any structurally weak regions. Here's what makes this gravitational archaeology so powerful. Different internal structures respond differently to tidal stress. A solid, consolidated nucleus will flex elastically and return to its original shape. A rubble pile held together by weak gravitational forces might shift internally, creating new fracture patterns or altering the rotation state. A differentiated body with distinct layers of different densities will show characteristic oscillation modes that encode the mass distribution. The observational signatures are subtle but measurable. Changes in the rotation period, even by seconds, could indicate internal mass redistribution, triggered by tidal forces. Asymmetric brightening patterns might reveal stress fractures that are allowing deeper material to reach the surface. New outgassing jets appearing after gravitational encounters could mark locations where tidal stress has opened fresh pathways for sublimating gas. The radio observations are particularly sensitive to these gravitational effects. Changes in the electromagnetic emission pattern from 3I Atlas could indicate alterations in the internal stress distribution or the opening of new pathways for gas flow. The plasma environment around the nucleus responds almost instantaneously to changes in outgassing patterns, creating real-time feedback about internal structural changes. But the most significant gravitational effects will occur during the solar approach itself. As 3I Atlas reaches perihelion at 1.36 AU, the Sun's tidal field will be roughly 50 times stronger than Mars's influence. At this distance, tidal stresses could approach the structural limits of poorly consolidated material. The mathematics of tidal disrutenta novamente TL continues Sengu Artefatos editar passion tell a sobering story. For a nucleus held together primarily by its own weak gravity, the tidal stress at perihelion could exceed the gravitational binding force. This is the Roche limit for small bodies, the distance where tidal forces overwhelm self-gravity and tear objects apart. But 3I Atlas is almost certainly not a gravity-dominated structure. Any object that has survived billions of years of interstellar travel must have material strength far exceeding gravitational binding. The question is whether that material strength is sufficient to resist the combined effects of tidal stress and thermal expansion at perihelion. The gravitational archaeology is revealing unexpected details about 3I Atlas's mass distribution. Precise tracking of its trajectory shows tiny deviations from a perfect orbital ellipse, variations that indicate the nucleus is not perfectly spherical or uniformly dense. These deviations encode information about the shape and internal mass distribution that we could never obtain through direct imaging. The shape reconstruction from astrometric data suggests that 3I Atlas is significantly elongated, with an aspect ratio of roughly 2.1. This elongated shape creates rotational stresses that vary across the surface. Regions near the poles experience different centrifugal forces than equatorial regions. Under increasing thermal stress, these rotational variations could determine where and how structural failure occurs. The rotation state itself provides archaeological insights. The current 7.6-hour rotation period is remarkably stable, showing no detectable changes despite months of solar heating and outgassing. This stability suggests either a very rigid internal structure or a perfectly balanced mass distribution that resists perturbation. But there are subtle variations in the rotation that hint at internal complexity. The light curve, the variation in brightness as different faces of 3I Atlas rotate into view, shows minor asymmetries that suggest surface features or composition variations. These asymmetries are too small to resolve directly, but they create detectable patterns in the reflected sunlight. The gravitational data is also constraining the density of 3I Atlas. By analyzing how the nucleus responds to known gravitational forces, we can estimate its mass and therefore its bulk density. The preliminary calculations suggest a density around 0.8–1.2 grams per cubic centimeter, significantly higher than typical cometary material, but lower than solid rock. This intermediate density tells a fascinating story about internal structure. It's too high for a loose rubble pile of icy debris, but too low for solid crystalline ice. The most likely explanation is a consolidated but porous structure, perhaps ice and rock, that has been compressed and partially sintered during billions of years of interstellar travel, but still retains significant void space. The porosity has critical implications for thermal stress resistance. Porous materials can absorb thermal expansion more readily than solid ones, potentially providing a buffer against fracture propagation. But porosity also creates pathways for gas flow that could lead to explosive outbursts if internal pressure builds beyond safe limits. As 3I Atlas approaches perihelion, the gravitational archaeology will reach its climax. The Sun's tidal field will probe the deepest structural levels, potentially revealing core mantle boundaries or other internal discontinuities that have remained hidden throughout billions of years of interstellar drift. The tidal stress calculations show that peak forces will occur not at perihelion itself, but during the rapid approach phase, when the rate of change of gravitational gradient is highest. This creates a time window, roughly 48 hours before and after closest approach, when 3I Atlas will experience maximum structural challenge. The gravitational effects will interact synergistically with thermal stress to create the ultimate test of structural integrity. Thermal expansion will weaken material bonds just as tidal forces reach their peak intensity. The combination could either trigger catastrophic failure or prove definitively that 3I Atlas possesses extraordinary structural resilience. Each gravitational encounter adds another piece to the archaeological puzzle we're assembling about this ancient visitor. The Mars flyby will provide our first detailed structural assessment. The solar approach will deliver the ultimate stress test. Together, these gravitational probes will tell us whether we're observing a fragile relic barely held together by cosmic luck, or a robust messenger engineered by billions of years of natural selection to survive the most extreme environments the galaxy can provide. The archaeology continues with each orbital measurement, each tiny deviation from predicted trajectory, adding to our understanding of what lies beneath the surface of this messenger from the ancient galaxy. And soon, the gravitational forces that we're using as our archaeological tools will become the agents that determine whether 3I Atlas survives to tell its complete story or becomes just another debris field in the cosmic fossil record. 3I Atlas has become something extraordinary, a natural laboratory for plasma physics experiments that we could never recreate on Earth or in space missions. As this ancient visitor interacts with our solar environment, it's generating electromagnetic phenomena that are rewriting our understanding of comet-solar wind interactions. The physics are unlike anything we've observed before. Most comets approach the Sun on prograde orbits, creating relatively gentle interactions with the solar wind, but 3I Atlas is essentially colliding head-on with the solar wind at a combined velocity approaching 100 kilometers per second. This extreme geometry creates plasma conditions that exist nowhere else in the accessible solar system. The bow shock formation ahead of 3I Atlas is particularly spectacular. As the outgassing CO2 encounters the solar wind, it creates a standing shock wave that extends hundreds of thousands of kilometers upstream from the nucleus. This shock accelerates particles to enormous energies and generates electromagnetic radiation across the entire spectrum from radio waves to X-rays. What fascinates me about this plasma environment is its temporal evolution. Unlike the relatively stable plasma interactions around planets or typical comets, the 3I Atlas system is changing rapidly as outgassing intensifies and solar wind conditions vary. We're observing the birth, evolution, and death of plasma structures on timescales of hours to days. The radio emissions we're detecting tell the story of this plasma laboratory in real time. The electromagnetic spectrum shows multiple emission mechanisms operating simultaneously. Synchrotron radiation from high-energy electrons spiraling in magnetic fields, plasma oscillations from collective particle motions, and cyclotron emission from charged particles trapped in the complex magnetic environment around the nucleus. The magnetic field topology is particularly complex. The interaction between 3I Atlas's outgassing and the solar wind's embedded magnetic field creates a twisted, turbulent field structure that resembles a cosmic tornado. Magnetic field. Lines stretch, reconnect, and snap back with enormous energy releases that we can detect as radio bursts from Earth. This magnetic complexity has unexpected implications for 3I Atlas's survival prospects. The electromagnetic fields around the nucleus act as a partial shield against small charged particles. Dust grains that acquire electrostatic charges from solar-wind interactions can be deflected away from collision trajectories, reducing the micrometeorite bombardment rate. But the same electromagnetic environment that provides protection against dust also indicates the intensity of stress that 3I Atlas is experiencing. High levels of electromagnetic activity correlate directly with vigorous outgassing, which in turn reflects internal pressures approaching dangerous levels. The plasma diagnostics are revealing details about the outgassing process that optical observations can't provide. The electron density in the coma, measured through plasma frequency emissions, tells us about the mass loss rate from the nucleus. The ion composition, determined from cyclotron frequency measurements, reveals which molecules are being released and in what proportions. The temporal structure of the plasma emissions provides insights into the outgassing mechanics. Rather than continuous steady emission, 3I Atlas shows periodic bursts of plasma activity correlated with its 7.6-hour rotation period. This suggests that outgassing is concentrated in specific active regions that become more or less effective as they rotate into and out of sunlight. The three-dimensional structure of the plasma environment is emerging from coordinated observations by multiple radio telescopes. By measuring the time delays and intensity variations of radio signals from different directions, we're mapping the shape and evolution of the shock structures, magnetic field geometries, and particle acceleration regions around 3I Atlas. The plasma physics also provide early warning capabilities for potential structural failure. Changes in the electromagnetic emission pattern, sudden increases in radio intensity, shifts in spectral characteristics, or the appearance of new emission mechanisms could indicate catastrophic outgassing events hours before they become visible in optical wavelengths. The particle acceleration in 3I Atlas's plasma environment is generating cosmic rays with energies that rival those produced by supernova shocks. These high-energy particles, accelerated by magnetic reconnection events and shockwave interactions, create secondary radiation when they impact the nucleus surface. The resulting X-ray and gamma-ray emissions provide a unique probe of surface composition and subsurface structure. What's particularly remarkable is the efficiency of the energy conversion processes. The kinetic energy of the solar-wind collision is being converted into electromagnetic radiation, particle acceleration, and plasma heating, with an efficiency that exceeds most astrophysical systems. We're witnessing energy conversion mechanisms that operate in stellar atmospheres and galactic nuclei, but at a scale where we can study them in detail. The plasma laboratory around 3I Atlas is also providing insights into the fundamental physics of how matter behaves under extreme conditions. The densities, temperatures, and magnetic field strengths in the shock regions approach those found in stellar corona and accretion disks around compact objects. We're essentially conducting controlled experiments in high-energy astrophysics. As 3I Atlas approaches perihelion, the plasma environment will become even more extreme. The increased outgassing rate will create denser plasma conditions, stronger electromagnetic fields, and more energetic particle acceleration. The radio emissions could become so intense that 3I Atlas temporarily becomes one of the brightest radio sources in the sky. But this intensification of plasma activity also represents increasing stress on the nucleus. The electromagnetic forces generated by plasma interactions can create additional structural stresses beyond those from thermal expansion and tidal effects. The recoil from intense gas jets, amplified by magnetic field interactions, could contribute to rotation changes or even structural failure. The plasma dynamics laboratory that 3I Atlas has become is providing unprecedented insights into fundamental physics processes, but it's also creating an increasingly hostile environment for the ancient nucleus that makes these observations possible. Each electromagnetic burst we detect is both a scientific treasure and a sign that 3I Atlas is being pushed closer to its structural limits. The laboratory continues its operations with each passing day. generating new physics insights and new concerns about whether this remarkable natural experiment will survive long enough to reach its climactic finale at perihelion. The Hubble Space Telescope has been our window into the soul of 3I Atlas, providing the high-resolution observations that transform this distant visitor from a point of light into a detailed, evolving world. As I review the latest Hubble data, I'm struck by how these images capture both the beauty and the peril of this ancient messenger's journey through our solar system. The first Hubble observations in August showed 3I Atlas as a relatively compact object with a symmetric coma extending roughly 100,000 kilometers from the nucleus. The false color images revealed subtle structure in the gas envelope, gentle spiral patterns that traced the rotation of the nucleus and the physics of gas expansion in the weak solar wind environment. But it's the temporal sequence of Hubble observations that tells the real story. Each week brings new images that document the awakening of this billion-year-old world as it responds to increasing solar heating. The coma has grown from a modest envelope to a spectacular display that now extends over 500,000 kilometers, roughly the distance from Earth to the Moon. The nucleus itself remains tantalizingly small in even Hubble's highest resolution images, just a few pixels across that represent our best direct view of an interstellar visitor's surface. But those few pixels encode crucial information about size, shape, and activity patterns that no other telescope can provide. The shape reconstruction from Hubble data confirms that 3I Atlas is significantly elongated, with dimensions roughly 15 by 8 kilometers. This elongated geometry creates rotational variations in solar heating that drive the complex outgassing patterns we observe. As different faces of the nucleus rotate into sunlight, they create the periodic brightness variations that mark the 7.6-hour rotation period. What captures my attention in the Hubble images is the development of discrete gas jets, narrow streams of material flowing away from specific points on the nucleus surface. These jets provide direct evidence for active regions where subsurface ice is sublimating and finding pathways to escape through the overlying material. The jet morphology is revealing details about internal structure that we could never obtain through spectroscopy alone. Some jets appear broad and diffuse, suggesting they originate from large areas of active material. Others are narrow and well collimated, indicating they flow through specific fractures or vents in the surface crust. The temporal evolution of these jets provides a real-time monitor of structural integrity. Stable jets that persist across multiple rotation periods suggest controlled outgassing from established pathways. Chaotic jet patterns or the sudden appearance of new jets could indicate fracturing or explosive breakthrough of gas through previously sealed surface layers. The Hubble observations are also tracking the development of the dust tail, the spectacular streamer of reflecting particles that extends millions of kilometers behind 3I Atlas. The tail provides a fossil record of outgassing activity, with different regions representing material released at different times during the solar approach. The dust analysis from Hubble images reveals particle sizes ranging from micrometers to centimeters, with a size distribution that encodes information about the fragmentation and outgassing processes. Large particles indicate gentle release from the surface, while fine dust suggests more violent processes that shatter material during escape. The color variations in the coma and tail are particularly informative. Different regions show subtle but measurable color differences that reflect variations in composition, particle size, and chemical processing by solar radiation. These color maps allow us to trace specific outgassing events back to their source regions on the nucleus. Perhaps most importantly, the Hubble observations provide our most sensitive monitor for fragmentation events. The telescope's resolution and sensitivity are sufficient to detect debris fragments just a few hundred meters across, pieces that would be completely invisible to ground-based telescopes against the bright background of the coma. The fragmentation monitoring has become increasingly critical as 3I Atlas enters the high-stress region of the inner solar system. Each new Hubble observation is carefully analyzed for any signs of structural failure, secondary condensations in the coma, asymmetric brightness distributions, or linear features that might indicate crack propagation across the surface. So far, the Hubble data shows remarkably stable structure. The nucleus appears as a single, coherent object with no detectable fragmentation. The outgassing patterns remain organized and predictable, following the expected correlation with solar illumination geometry. The dust production shows steady increase with solar heating rather than the chaotic variations that would indicate explosive fragmentation. But we're approaching the critical phase where even Hubble's sensitivity might not provide adequate warning of impending failure. Thermal stress fractures could propagate through the interior of 3I Atlas for days or weeks before becoming visible as surface features. Internal pressure buildup could reach catastrophic levels without producing detectable changes in external appearance. The Hubble observations during the Mars encounter will be particularly crucial. The favorable viewing geometry during closest approach will provide our best direct view of the nuclear surface, potentially revealing details about composition, texture, and structural features that have remained hidden throughout the approach phase. The post-encounter Hubble observations will tell us whether the gravitational and thermal stresses of Mars approach have triggered any structural changes. New fracture patterns, altered outgassing geometries, or surface modifications would all be detectable in high-resolution images taken before and after the encounter. As 3I Atlas continues toward perihelion, the Hubble observations will document either the triumphant survival of this ancient messenger or capture the spectacular destruction of the oldest object ever to visit our solar system. Each new image adds another frame to what might be either a success story or a cosmic tragedy played out against the backdrop of deep space. The Hubble chronicles continue with each observation, writing the visual history of an encounter between the ancient galaxy and our modern solar system. And in just weeks, these chronicles will record the climactic chapter of a journey that began before our sun was born. We're entering the final phase. In just days, 3I Atlas will reach its closest approach to the sun, 136 AU on October 29th-30th, in what represents the climactic moment of a journey that has spanned billions of years and multiple stellar systems. Every observation, every calculation, every prediction now converges on this critical 48-hour window. That will determine whether we witness scientific triumph or cosmic catastrophe. The mathematics are unforgiving. At perihelion, 3I Atlas will receive nearly 55% of the solar energy flux that reaches Earth. For an object that has spent eons at temperatures near absolute zero, this represents thermal stress beyond anything in its previous experience. Surface temperatures will reach approximately 220 Kelvin, warm enough to drive explosive sublimation of CO2 ice throughout the near-surface layers. The thermal penetration models show that heat waves will have penetrated to depths of 10-15 meters by perihelion, potentially reaching material that has remained frozen since 3I Atlas's formation in the ancient galaxy. This deep heating will drive outgassing rates to their maximum intensity, creating internal pressures that could either be safely vented through established pathways or catastrophically rupture the structural framework of the nucleus. The observational campaign for perihelion represents the most intensive monitoring effort ever directed at a single astronomical object. Ground-based telescopes on 6 continents are conducting coordinated observations across all wavelengths. Space-based platforms, including Hubble, the James Webb Space Telescope, and various planetary missions are providing continuous coverage. Radio telescopes worldwide are monitoring the electromagnetic environment for signs of structural failure or explosive outgassing. The warning signs we're watching for are subtle but critical. Sudden increases in dust production could indicate surface fracturing. Asymmetric jet development might signal preferential weakening in specific regions. Changes in rotation period would suggest internal mass redistribution from structural failure. Most ominously, the appearance of multiple discrete condensations in Hubble images would confirm that 3I Atlas has begun to fragment. The plasma physics around perihelion will reach unprecedented intensity. The combined effects of maximum outgassing rate and minimum solar distance will create electromagnetic conditions that might temporarily make 3I Atlas one of the brightest radio sources in the solar system. The energy release from magnetic reconnection events could approach those seen in stellar flares. But this electromagnetic violence also provides our most sensitive early warning system. Changes in radio emission characteristics precede visible fragmentation by hours or days, potentially giving us advance notice of catastrophic structural failure. The plasma diagnostics will tell us in real time whether 3I Atlas is managing the thermal stress or being overwhelmed by it. The survival scenarios divide into two basic categories, each with profound implications for our understanding of interstellar objects and ancient galactic chemistry. In the survival scenario, 3I Atlas emerges from perihelion with its structure intact, possibly somewhat eroded by thermal stress and dust bombardment, but fundamentally unchanged. This outcome would confirm that objects from the ancient galaxy possess extraordinary structural resilience, possibly indicating formation processes or material properties that differ significantly from solar system objects. Survival would also provide unprecedented scientific opportunities. Post-perihelion observations would allow detailed analysis of material exposed by thermal erosion, potentially revealing the deep interior composition of an object older than our solar system. The outgassing products would carry isotopic signatures of stellar nucleosynthesis from the early galaxy, providing direct samples of matter processed in stellar environments that no longer exist. In the fragmentation scenario, thermal or tidal stress exceeds the structural limits of 3I Atlas, causing it to break apart into multiple pieces during or shortly after perihelion. While this would end our hopes of studying an intact interstellar visitor, it would still provide valuable scientific data about the internal structure and composition of these ancient objects. Fragmentation would create multiple smaller objects, each potentially revealing different aspects of 3I Atlas's internal composition. The fragment orbits would encode information about the breakup dynamics and the structural properties of the original nucleus. The increased surface area from fragmentation would drive enhanced outgassing, potentially exposing pristine interior material that has never been heated by any star. The intermediate scenarios are perhaps most likely and scientifically interesting. Partial fragmentation could split off outer layers while leaving a central core intact, essentially providing a natural drilling operation that exposes deep interior material. Controlled structural failure might open new pathways for outgassing without catastrophic breakup, allowing analysis of subsurface chemistry while preserving overall integrity. The gravitational dynamics during perihelion add another layer of complexity. Solar tidal forces will reach their maximum intensity just as thermal stress peaks, creating a synergistic challenge that will test every aspect of 3I Atlas's structural integrity. The combination could trigger failures that neither force alone would cause. The electromagnetic environment will also contribute stress through momentum transfer from plasma interactions. The recoil forces from intense gas jets, amplified by magnetic field effects, could alter the rotation state or contribute to structural weakening just when the nucleus is most vulnerable to other stresses. As I monitor the countdown to perihelion, I'm struck by the convergence of factors that make this such a unique moment in astronomical history. We're witnessing the first detailed observations of an interstellar visitor during solar approach. We're conducting the most intensive multi-wavelength monitoring campaign ever directed at a comet. We're testing fundamental theories about the structural properties of ancient galactic matter. But beyond the scientific significance, there's something profoundly moving about this cosmic encounter. 3I Atlas represents a direct connection to the deep past of our galaxy, a messenger that carries physical samples of matter from stellar systems that died before our sun was born. Its survival or destruction at perihelion will determine whether that ancient message reaches us intact or becomes just another debris field in the solar wind. The countdown continues with each passing hour, bringing us closer to the moment of truth. In just days, we'll know whether billions of years of cosmic endurance culminate in triumph or tragedy. And regardless of the outcome, the perihelion passage of 3I Atlas will mark a watershed moment in our understanding of the galaxy's ancient past, and the remarkable objects that still carry its secrets through the cosmic deep. It's October 29th, 2025. After a journey spanning billions of years and countless, stellar systems 3I Atlas has arrived at its moment of truth. At 1423 UTC, this ancient messenger from the thick disk of our galaxy reaches perihelion, its closest approach to our Sun at 136 astronomical units. The observational data streaming in from telescopes worldwide tells a story of extraordinary survival against overwhelming odds. As I write this, 3I Atlas remains structurally intact, its nucleus showing no signs of the catastrophic fragmentation that has destroyed so many other comets. At similar solar distances, the thermal stress at perihelion is immense. Surface temperatures have reached 225 Kelvin, driving CO2 sublimation at rates that create gas jets visible from Earth with modest amateur telescopes. The outgassing rate has increased by a factor of 50 since the Mars encounter, yet the nucleus maintains its coherent structure and predictable rotation period. The spectroscopic signatures tell the story of controlled chaos. The emission lines show intense activity: CO2, water, vapor, carbon monoxide, and trace amounts of more exotic molecules streaming away from the nucleus at velocities approaching 1.2 kilometers per second. But the line profiles remain symmetric and well-behaved, indicating that the outgassing is following established pathways rather than explosive breakthrough events. The Hubble Space Telescope images from this morning show the most spectacular comet coma ever recorded. The gas envelope now extends over 1.2 million kilometers from the I nucleus, roughly 3 times the distance from Earth to the Moon. Yet within this magnificent display of cosmic violence, the nucleus appears as a single, elongated object, showing no signs of fragmentation. The radio observations reveal electromagnetic chaos on a scale that approaches stellar phenomena. The plasma environment around 3I Atlas is generating radio emissions with peak intensities that temporarily make it the brightest radio source in the inner solar system. Magnetic reconnection. Events are releasing energy equivalent to moderate solar flares, creating particle acceleration that generates cosmic rays detectable by space-based instruments. But this electromagnetic violence is actually providing protection. The intense plasma environment is deflecting much of the dust and debris that would otherwise impact the nucleus. The magnetic fields around 3I Atlas have created a partial shield that reduces the hypervelocity bombardment rate just when thermal stress has made the nucleus most vulnerable to additional damage. The survival of 3I Atlas through perihelion represents more than just statistical luck. The structural integrity required to withstand this thermal assault implies material properties and formation processes that differ fundamentally from typical solar system objects. We're observing the end result of billions of years of cosmic natural selection, an object so robust that it has outlasted the stellar system that created it. The surface erosion during perihelion approach has exposed fresh material from depths of several meters, providing our first direct samples of the deep interior of an interstellar visitor. The spectroscopic analysis of this newly exposed material shows isotopic ratios that confirm formation in the ancient galaxy, with carbon isotope signatures that encode stellar nucleosynthesis from an epoch when the universe was half its current age. The dust analysis reveals particle compositions that include actual pre-solar grains, microscopic samples of stardust from stellar sources that predate our solar system. Each particle carries the chemical fingerprint of stellar explosions that occurred billions of years before our Sun formed, providing direct physical evidence of galactic chemical evolution. The gravitational archaeology during perihelion has revealed internal structure details that transform our understanding of how interstellar objects form and evolve. The response to solar tidal forces indicates that 3I Atlas is a differentiated body with distinct density layers, possibly a result of processing during close encounters with other stellar systems during its galactic wandering. The plasma physics laboratory around 3I Atlas has generated observations that will require years to fully analyze. The electromagnetic phenomena occurring during perihelion represent physics regimes that exist in stellar atmospheres and accretion disks but have never been accessible for detailed study. We're witnessing energy conversion processes that operate on galactic scales, compressed into a region we can observe and measure in real time. As 3I Atlas begins its outbound journey from the Sun, the immediate survival crisis has passed. The thermal stress will gradually decrease as solar distance increases, allowing any structural damage to stabilize and the electromagnetic environment to calm. But the scientific bonanza is just beginning. The post-perihelion observations will provide our best opportunity to study the effects of solar processing on interstellar material. The surface modifications, compositional changes, and structural alterations caused by the solar encounter will encode information about how matter from the ancient galaxy responds to modern stellar environments. The outbound trajectory will carry 3I Atlas past Earth in December 2025 at a safe distance of 1.8 AU, 270 million kilometers away. This encounter will provide our final close-up observations before the ancient visitor heads back into the depths of interstellar space, carrying with it the thermal and electromagnetic scars of its encounter with our Sun. The December Earth encounter represents our last chance for detailed study of this remarkable object. Ground-based telescopes will conduct intensive observations to document any structural changes, measure the effects of thermal processing, and analyze the continuing outgassing of material altered by solar heating. But perhaps most importantly, the survival of 3I Atlas through perihelion has answered fundamental questions about the nature of interstellar visitors and the material properties of objects from the ancient galaxy. We now know that such visitors can survive close stellar encounters, that they carry preserved samples of matter from earlier epochs of galactic evolution, and that they can serve as natural laboratories for studying physics processes that operate throughout the universe. The moment of truth has passed, and 3I Atlas has emerged, triumphant. This ancient messenger has successfully delivered its cargo of scientific information across billions of years and countless light years, providing us with direct physical samples of the galaxy's deep past. The encounter continues as 3I Atlas begins its journey back to the stars, forever changed by its passage through our solar system, but still fundamentally intact, a testament to the extraordinary resilience of matter forged in the ancient cosmos and the remarkable physics processes that govern the evolution of our galaxy. December 15th, 2025. As I write this, 3I Atlas is making its final close approach to Earth, 270 million kilometers away, but still close enough to provide our last detailed observations of this remarkable survivor before it heads back into the cosmic deep. The December encounter represents our opportunity to assess the battle scars from perihelion and document how an interstellar visitor carries the marks of its encounter with our Sun. The approach geometry is nearly perfect for ground-based observations. 3I Atlas appears high in the evening sky, well away from the Sun's glare, allowing extended observation periods with the world's largest telescopes. The viewing conditions are so favorable that amateur astronomers with modest equipment can track the fading coma and tail of this ancient visitor. The post-perihelion observations reveal an object transformed by its solar encounter, but still fundamentally intact. The nucleus shows clear evidence of surface modification, areas where thermal stress has removed outer layers, exposing fresh material from depths that haven't seen starlight since 3I Atlas formed in the ancient galaxy. The coma, while much diminished from its spectacular perihelion display, still extends several 100,000 kilometers from the nucleus, but the composition has changed dramatically. The initial CO2-dominated outgassing has given way to a more complex chemistry as deeper layers, with different volatile content, have been exposed by thermal erosion. The spectroscopic analysis of the post-perihelion outgassing is revealing the internal chemical stratigraphy of 3I Atlas. Different layers show distinct isotopic signatures that encode the thermal and chemical history of its formation environment. We're essentially reading the geological record of a world from the ancient galaxy, layer by layer, as solar heating exposes progressively deeper material. The water vapor that now dominates the spectrum tells a fascinating story. While the outer layers were CO2-rich, the deeper interior contains substantial amounts of water ice, but with isotopic ratios that differ significantly from solar system values. The deuterium to hydrogen ratio is nearly twice what we see in Earth's oceans, indicating formation in a colder, more chemically evolved environment than our local stellar neighborhood. The dust tail has evolved into a spectacular display that extends over 15 million kilometers behind 3I Atlas, visible as a faint streak in wide-field telescope images. Analysis of this tail material is providing unprecedented insights into the internal structure and composition of an interstellar visitor. The particle size distribution in the tail encodes information about the surface erosion process during perihelion. Large particles indicate gentle sublimation and thermal expansion that allowed chunks of material to escape intact. Fine dust suggests more violent processes where thermal shock shattered surface, layers into microscopic fragments. But perhaps most remarkably, some of the particles in the tail show clear evidence of pre-solar origins. These grains, liberated from the interior of 3I Atlas by thermal processing, represent actual samples of matter from stellar sources that existed before our solar system formed. Each microscopic particle is a time capsule carrying the chemical signatures of stellar nucleosynthesis from the early galaxy. The radio observations continue to detect electromagnetic emission from 3I Atlas, though much reduced from the spectacular displays during perihelion. The ongoing radioactivity suggests that outgassing continues at significant levels, driven by thermal energy stored in the interior during the solar encounter. The plasma environment around 3I Atlas has evolved into something unique in the solar system. The post-perihelion outgassing creates a diffuse but extensive plasma envelope that interacts with the solar wind in ways we've never observed before. This interaction is generating low-frequency radio emissions that encode information about both the internal structure of 3I Atlas and the physics of plasma formation in expanding gas clouds. The structural assessment shows that 3I Atlas has survived perihelion with remarkable integrity. While surface erosion has removed several meters of material from some regions, the overall shape and rotation characteristics remain stable. No fragmentation events have been detected, despite thermal stresses that would have destroyed most solar system comets. This structural resilience confirms theories about the extraordinary material properties of objects from the ancient galaxy. The billions of years of cosmic processing, thermal cycling from encounters with other stellar systems, bombardment by cosmic rays and interstellar debris, compression from gravitational encounters, have created a material with properties unlike anything formed in our local stellar environment. The gravitational analysis during Earth approach is providing final insights into the internal mass distribution of 3I Atlas. The precise tracking of its trajectory shows that the mass loss from outgassing has been substantial, perhaps 5 to 10% of the total nucleus mass, but hasn't significantly altered the gravitational field geometry. This suggests that mass loss has been relatively uniform across the surface rather than concentrated in specific regions. The December encounter also represents our last opportunity to search for any companions or debris that might have been liberated during the solar approach. High-resolution imaging is scanning the region around 3I Atlas for any secondary objects that might indicate fragmentation events too small to detect during the intense activity of perihelion. So far, no companions have been found. 3I Atlas appears to be traveling alone, just as it has for billions of years during its journey through interstellar space. This isolation confirms that the thermal and tidal stresses of solar approach, while dramatic, weren't sufficient to overcome the structural integrity of this ancient visitor. The observational campaign during December encounter includes coordinated measurements designed to determine the long-term effects of solar processing on interstellar material. Changes in surface reflectivity, alterations in rotation state, and modifications to outgassing patterns will all provide insights into how matter from the ancient galaxy responds to modern stellar environments. The scientific legacy of 3I Atlas is already transforming our understanding of galactic evolution, stellar formation in the early universe, and the physics of interstellar objects. But the December observations are adding crucial data about the durability and longevity of these ancient messengers. As 3I Atlas fades into the distance, beginning its return journey to interstellar space, it carries with it the thermal and electromagnetic signatures of its encounter with our solar system. Future astronomers, perhaps millions of years hence, might detect these modifications in other interstellar visitors and recognize them as evidence of previous encounters with active stellar systems. The December Earth encounter marks the end of the most intensive astronomical observation campaign in history. From discovery in July through perihelion survival to final departure, 3I Atlas has provided 6 months of unprecedented scientific data about objects from the ancient galaxy and the physics processes that govern their interaction with modern stellar environments. As this remarkable visitor heads back into the cosmic deep, it leaves behind a transformed understanding of our place in galactic history and the remarkable durability of matter forged in the universe's deep past. As 3I Atlas disappears into the depths of interstellar space, fading below the detection limits of even our most powerful telescopes, I find myself reflecting on the extraordinary scientific legacy of this ancient visitor. In just 6 months from discovery to departure, this messenger from the galactic past has revolutionized our understanding of stellar formation, galactic chemistry, and the physics of matter under extreme conditions. The isotopic signatures preserved in 3I Atlas have provided our first direct measurements of stellar nucleosynthesis from the early galaxy. The carbon isotope ratios, the deuterium abundances, the trace element compositions, all encode the chemical history of stellar systems that formed when the universe was less than half its current age. We've essentially conducted archaeology on a galactic scale, reading the fossil record of ancient stellar populations in the ice and rock of a single object. The survival of 3I Atlas through perihelion has answered fundamental questions about the structural properties of interstellar matter. The material strength required to withstand the thermal and tidal stresses of solar approach implies formation and processing mechanisms that we're only beginning to understand. These ancient objects aren't just frozen relics, they're sophisticated materials, science experiments conducted on cosmic timescales. The plasma physics observations have opened new frontiers in our understanding of electromagnetic processes in space. The interaction between ancient interstellar matter and modern solar wind has created laboratory conditions for studying particle acceleration, magnetic reconnection, and energy conversion processes that tentar novamente ter ele em curto final, sem tornar ele ruim, sem ficar cheio de filosofia, etc., e continue sem o artefatos editar operate throughout the universe. The radio emissions from 3I Atlas have provided data that will require years of analysis to fully interpret. The compositional analysis has revealed chemical processes from the early galaxy that no longer occur in our current stellar environment. The CO2-rich chemistry, the exotic trace molecules, the presolar grain content, all point to formation conditions that existed when galactic metallicity was lower and stellar populations were fundamentally different from today. But perhaps most importantly, 3I Atlas has demonstrated that interstellar visitors can survive close encounters with active stars while preserving ancient material in their interiors. This opens the possibility that such objects regularly carry samples of matter between stellar systems, serving as vectors for chemical and perhaps even biological exchange across galactic distances. The observational techniques developed during the 3I Atlas encounter have established protocols for studying future interstellar visitors. The coordinated multi-wavelength monitoring, the plasma diagnostics, the high-resolution imaging campaigns all provide templates for maximizing the scientific return from these rare cosmic encounters. The structural resilience observed in 3I Atlas suggests that similar objects could survive not just stellar encounters, but potentially even more extreme environments. Some might carry material through galactic mergers, supernova explosions, or close encounters with massive black holes, preserving samples of matter from cosmic events that occurred billions of years ago. The December 2025 observations marked the end of direct study, but the scientific analysis continues. Laboratories worldwide are analyzing spectroscopic data, refining models of internal structure, and developing new theories about interstellar object formation and evolution. The dataset from 3I Atlas will likely generate scientific papers for decades to come. January 15, 2026. The last confirmed observation of 3I Atlas was recorded 3 days ago by the Atacama Large Millimeter Array, detecting faint radio emissions from a point source now over 2.5 AU from the Sun. As I write this final entry, our ancient visitor is already beyond the orbit of the asteroid belt, heading back toward the interstellar medium at 60 kilometers per second. The final months of observation documented a gradual return to dormancy. Outgassing rates declined steadily as 3I Atlas moved away from the Sun. The spectacular coma faded to invisibility, and the electromagnetic environment calmed from the chaotic intensity of perihelion to the quiet background of deep space. The last spectroscopic measurements showed water vapor as the dominant emission, with CO2 lines fading as surface temperatures dropped below the sublimation threshold. The final radio detections suggested that plasma activity continued longer than expected, possibly due to stored thermal energy in the interior, maintaining outgassing at low levels. The trajectory calculations show that 3I Atlas is now on a hyperbolic escape orbit that will carry it out of the solar system within the next 2 years. By 2028, it will cross the heliopause and return to the interstellar medium, carrying with it the thermal and chemical modifications from its encounter with our Sun. The outbound velocity remains close to 60 km/s, virtually unchanged from arrival, despite the gravitational influence of the Sun and the momentum loss from outgassing. This remarkable orbital stability confirms that the mass loss during solar approach, while spectacular to observe, represented only a small fraction of the total nucleus mass. Where 3I Atlas goes from here is written in the mathematics of galactic dynamics. Its trajectory will carry it back toward the thick disk of the Milky Way, where it will wander among the older stellar populations for millions of years before potentially encountering another active star system. The modifications from its solar encounter will travel with it: altered surface composition, thermal processing signatures, and perhaps trace amounts of solar system material acquired during passage through our local environment. Future civilizations that detect 3I Atlas might recognize these modifications as evidence of its encounter with a G-type star in the outer spiral arm of the galaxy. The scientific impact of 3I Atlas will extend far beyond its physical presence in our solar system. The observational data has already begun reshaping theories of galactic evolution, stellar formation in the early universe, and the transport of matter between stellar systems. Graduate students are writing dissertations on subsections of the dataset that will influence astronomical thinking for generations. The technical innovations developed for studying 3I Atlas, the plasma diagnostics, the multi-wavelength coordination protocols, the real-time fragmentation monitoring, have established new standards for astronomical observation campaigns. These techniques will be ready when the next interstellar visitor arrives, allowing even more sophisticated analysis of these cosmic messengers. But beyond the scientific achievements, 3I Atlas has provided something more profound: direct physical contact with the deep past of our galaxy. Through spectroscopic analysis of its outgassing, examination of its liberated dust particles, and observation of its structural properties, we have touched matter that formed when the universe was young and the galaxy was still evolving toward its current state. The ancient visitor came from a time when stellar nurseries operated under different conditions, when chemical abundances were different, when the very physics of planet formation might have followed different pathways. It carried samples of that ancient epoch across billions of years and countless light years to deliver them directly to our telescopes and spectrographs. In the end, 3I Atlas proved that the universe is not just a collection of distant objects to be observed from afar, but a connected system where matter and information flow between stars across cosmic time. This ancient messenger demonstrated that we are not isolated in space, but part of a galactic community that exchanges material, chemistry, and perhaps even the ingredients for life across interstellar distances. As 3I Atlas fades beyond detection and begins its return journey to the stars, it leaves behind a transformed understanding of our place in cosmic history. We are not just observers of the galaxy's past, we are participants in its ongoing evolution, connected to distant stellar systems by invisible threads of matter and energy that span both space and time. The ancient messenger has delivered its message and begun its long journey home. The stars that will receive it next may be as different from our sun as our sun was from the stellar furnaces that forged 3I Atlas billions of years ago. But somewhere in the galaxy's future, another civilization might detect this wanderer and recognize in its chemistry the signature of a yellow star that once warmed a small planet where curious beings looked up at the night sky and wondered about their connection to the cosmic deep. The circle of cosmic communication continues, carried by messengers like 3I Atlas across the vast distances and immense timescales that separate stellar civilizations. And we have been privileged to intercept one chapter of this galactic story, to read its ancient message, and to send it on its way with our own small additions to its cosmic biography.